right. Good morning, everybody. Hope we're all doing okay. Today we're going to be talking a little bit about something called kinetic molecular theory. All right, let me say it again. Kinetic molecular theory. It sounds very scientific, I know, but we can actually break it down and really see what it's talking about without even diving into it. All right? So first question, can anybody tell me what the word kinetic means? Yes, that's right. It's talking about movement. Right? Anything with movement is kinetic. Okay, think about a roller coaster, right? As a roller coaster is going down the hill, right, and going through the loops and going all around the bends, it has kinetic energy. It's kinetic. It's moving around. If you're throwing a ball through the air, that's kinetic. It's moving around. Anything with movement has kinetic energy. Let's look at molecular. What is molecular talking about? What does molecular mean? Can anybody tell me? That's good. Yes, yes. Dealing with anything with molecules or particles. They're very small. Good. So, theory. That's just a word scientists use to sound fancy. Whoops. Theory. So, we have kinetic molecular theory, or, if we look at it this way, moving particles theory. Right? So, kinetic molecular theory. What are we talking about when we talk about kinetic molecular theory? What we're really looking at is a few set of laws, or a few set of rules. Let me go ahead and erase this board. So first, kinetic molecular theory only deals with, and what we're talking about right now, we only want to work with behavior of particles and gases. Okay? Kinetic molecular theory tells us that all particles in gases are always moving around. Okay? It's always moving around. Let me show you that real quick. I have a balloon right here. I blew a bunch of gas into it. I filled it up. These molecules, my air molecules that I put in there, they don't just sit around, all right? They go in there and they start bouncing off of each other. They start moving around. Bouncing off of each other, they're bouncing off of the walls. That's kinetic molecular theory. It's always moving around. It's always changing. The gas is always moving around. We can even bring this into other states of matter. Like say we're looking at a liquid, right? I have a cup here. Or a bucket. And I fill it up with water. Are those particles, are those molecules moving, or are they staying still? That's right, they're always moving. They're always bouncing off of each other. It's always changing. None of it is staying the same. It's always moving. That's kinetic molecular theory. All right, let's look at this. I have a cube. All right? I got a cube right here. There's particles that make up the cube. Are those particles moving or are they staying still? That's right, they're moving. Even in solids, the particles are always moving. Right? Now granted, in a solid, the particles are closer together, so you don't really see that movement as much. But it's always vibrating. The solid is always shaking. There's always movement. It's kinetic molecular theory. It's true for all states of matter. Let's look at the next thing. Let's look at why it's true. It's true, kinetic molecular theory is true because everything is made of tiny particles, right? I'm made of tiny particles. This board is made of tiny particles. Paper towel, tiny particles. Everything is made up of tiny particles, right? The electrons and the protons come together to create the elements. The elements come together to create everything that you see here today. I don't even know what element this is, but it's something with elements in it, and it's all dealing with tiny particles, right? So, this box of vinyl gloves, does it have tiny particles that make it up, or is it just a box? Yeah, it's pretty easy. It's tiny particles. The tiny particles make up everything. And that is why the kinetic molecular theory holds true in all states of matter. Let's look at what we were just talking about. Those particles are constantly in motion, even in solids. We already described this. We already said this. This is a law. The particles collide with each other and the walls of their container elastically. That's a new word right here, elastically. It's a word you don't see much in chemistry, but you actually see it a lot in physics. Let's talk about what elastically means. Elastic. The elastically is describing collisions, okay? When something collides, you can either call it elastic or inelastic. Let me show you an example.
Go.
Like a rocket. Super Ball. Look, it's almost alive. It bounces and bounces, keeps going and going almost forever. Hurry, try and catch it. Super Ball is a mystery ball of 1,000 bounces, with many more bounces than any ball you ever owned. It is a super ball. It zigs and it zags. Fast bounce, high bounce. The most amazing ball ever created by science. Energized Super Ball is now in your hands. With amazing rebound, Super Ball actually bounces over a house. Now, watch Super Ball carefully in slow motion. Strange, weird, makes every bounce a game. Every game more magical. And it's still bouncing. Hurry, discover your new power with Super Ball. Under $1 wherever toys are sold.
I've got my Super Ball!
By Whammo.
So, unfortunately, we don't have access to the Super Ball. I really want one. But the Super Ball, what we just showed you, is an example of a very elastic collision. Okay, let me show you an example of an inelastic collision. Right? I have a ball right here, and I'm going to drop it on the table. Ready? It didn't bounce. Okay? Now, let's show an example of something that's a little bit more elastic. Ready? See, that one bounced some. Okay? Let me show you this again. Together. We have an inelastic and an elastic. Can you tell me which one was a more elastic collision? That's right. The bigger ball was more elastic. It bounced up. See, an elastic collision is a conservation of energy. Okay? Elasticity means it conserves energy. What does it mean to conserve energy? Is it wasted upon an impact, or is it just simply transferred over to the next object during the impact? That's right. If it conserves energy, it's easily transferred over and there's no energy lost. When we talk about kinetic molecular theory, we are saying that every particle, every collision that's happening inside of the container, especially when we deal with gases, is elastic, right? So every collision between a particle and another particle is just a simple transfer of kinetic energy, and there's no energy lost whatsoever. That is how we use the elasticity, right? And this is only to deal with ideal gases, right? We don't really necessarily deal with any other gases that aren't ideal. An ideal gas means that it's not polar. What does polar mean? That's right, it means that there's an attractive force, where there's two different sides. So in an ideal gas, there's no polarity, there's no other force besides the kinetic energy inside of the container. All right, let's move on. The average kinetic energy of all of these particles is the temperature. This is something we've been hinting at this entire unit, right? We've been talking about, let me erase this. We've been talking about using Kelvin, right? We all know to use Kelvin. But Kelvin is on a scale where at the very bottom, it's 0 degrees Kelvin. Can anybody tell me what 0 degrees Kelvin is called? That's good. Absolute zero. That's right. So at absolute zero, that means that there is no movement. There's no particle movement. This is the coldest anything theoretically can get. Our temperature is part of the kinetic energy. The kinetic energy is part of the temperature. It's the same thing. So, let's try this. If I was to raise the temperature, right? Our T is our temperature. If I was to raise the temperature of a gas in a container, what would happen to the kinetic energy in that container? If I was to raise the temperature, what would the kinetic energy do? That's exactly right. The kinetic energy will increase. It'll rise with the temperature. Let's try this. Let's say I lower the temperature. Okay, I bring the temperature down. What happens to the kinetic energy? Exactly. The kinetic energy also decreases. It also goes down along with it. This is to show, and this is really what temperature is, it's the kinetic energy of whatever you're observing. Okay? And this is also why we use Kelvin, because at the very bottom of Kelvin, there's no energy, and it is completely still. All right. Last but not least, let me bring this up some. Let's look at the very bottom here. It says that experience elastic collision and express no attraction for each other. This is what I just mentioned earlier on, right? Any gas, and we're talking about ideal gases here. An ideal gas, we'll say there's an ideal gas filled up with this balloon. An ideal gas is not polar, okay? And this is something that was in the very beginning of class when we talked about polarity, but it is not polar, okay? So if I was to ask you this question, is an ideal gas polar? You'd be able to say, no, that's right. There's no polarity, there's no extra forces, there's no electromagnetic forces, there's no dipole force, there's nothing going on in there. It's just simply elastic collisions. That's it. And that's all you have to worry about. And to finish off, let's look at this right here. This is the formula commonly used for kinetic energy of an object, okay? This is saying 1/2 times the mass of the object times its velocity squared. That's normally how we measure kinetic energy. This is just useful to know. Example is like, the faster, let's say this. I have an object, and I increase the speed, right? I increase the speed. The V goes up. What's going to happen to the kinetic energy? That's right, it also goes up. So the velocity and the kinetic energy are related, directly related, in the exact same way that the temperature and the kinetic energy are related. More temperature, more velocity, more kinetic energy. Less temperature, less velocity, less kinetic energy. That is kinetic energy molecular theory.